Thank you for that introduction. So I'm Colin Swaney, at Data-Driven Social Science Initiative. I'm going to talk about NetworkHawkes processes. Like so many Julia packages, the name kind of says it all. We got networks, Hawkes processes, and Julia. I struggled with a good introduction, and then I was looking through the schedule and I realized I already wrote a really good introduction in the abstract. So I'm just going to read it. NetworkHawkes processes. It's a pure Julia framework. You can define, simulate, and perform inference on a pretty general class of Bayesian probabilistic models. The key thing is that you can simultaneously perform inference on the structure of a network and an event-generating process. So the two things are combined. This is a framework that was developed by Scott Linderman and some co-authors at Harvard, now Princeton, in 2016. So the key feature of the event-generating process is that it's auto-regressive and a multi-variate. And then you have connections between nodes given a network structure, and that can be just any standard Bayesian network model that you like. So we combine these things together. It gives us a disciplined way of discovering latent network structure from the event data itself. This can be used in neuroscience, finance, whatever. It's a very general type of model. So I'm going to quickly talk about the package features, and then I'll go into detail on some of these later. So we have a modular design. I've tried to make this so that it would support extensions. If you want to bring your own component, you can do that. It supports both continuous time and discrete time models. It implements simulation via a Poisson thinning process, which I'll talk about. It provides multiple inference methods for all models and accelerates estimation using Julia's built-in multi-threading module. So I'm going to break this into sort of two parts. First, I'm going to describe what the NetworkHawkes process is, how it works, and go through a kind of recipe. And then I'll switch over to the features of the package. So Hawkes process is a Poisson process. It's modeling the arrival of events. And a Poisson process is basically defined by an intensity, which is lambda here. The intensity is essentially telling you how likely it is for an event to occur in a particular period of time. The defining feature of a Hawkes process is that it's auto-regressive. Every time an event occurs, there's an impact on the future intensity. It increases that. And in this framework, since it's a network, it potentially impacts the intensity on nodes around it as well. So there's an example here, which is a bivariate example. You have a red, one node has a red intensity, the other is given in blue. And what you see is towards the beginning there, you get this sort of spike in the intensity on the red node. And that's because you see every one of the small spikes as an event. So you have a number of events occurring on both the red node and the blue node, both of those contributing to the intensity on the red node. So Hawkes processes are good at capturing events where there tends to be spikes or clustering of events. And notice that the intensity is broken into two parts here. So there's a lambda naught, and then there's the sum of H terms. So the lambda naught is called the baseline or background process. It could be a simple homogeneous process with a constant intensity, or it could be something more complex, such as a log Gaussian Cox process, which is a basically exponentiated Gaussian process, so something very flexible. The key here is really that the baseline is largely independent of the rest of the model. So we can sort of pick whatever we want for the baseline. It's going to generate its own events and just do its own thing. All right, so what's the effect of each event? That's captured in an impulse response. An impulse response is essentially just a probability distribution. The traditional one is an exponential distribution, one parameter model. It results in an instantaneous increase in the intensity, which decreases exponentially. A more flexible model is the logistic normal or logit normal distribution, which has two parameters, a mean and a precision. And this allows you to move around this peak. So you can move the mean and adjust where the peak is. You can move the precision and determine how spiky or smooth this impulse response is going to be. The key thing here, though, is that the impulse response is only determining the timing of the effect of each event. Both of these are probability distributions. Anything that you would use should be a probability distribution. It integrates to one, and therefore the overall impact on future events is the same. So in order to have differences in connections between nodes, we need to do some sort of scaling. And we handle the scaling in what's called a spike and slab fashion. So we're going to sort of separate the scaling into two parts. The first part is a binary adjacency matrix, A. Every element in the matrix represents a connection from one node to another node. And then the second part is a weight matrix, a positive weight matrix. The weight matrix captures the strength or the magnitude of a connection from one node to another. So multiplying those together and you get the overall scale. And so if you put everything together, you have an impulse response multiplied times A times W. That's going to represent the overall effect of one node, an event occurring on one node on the intensity of another node. So that's almost everything in the Hawkes process. The last part is the network. So the adjacency matrix doesn't come out of thin air. We want a model to tell us where does that come from. And that model can be basically any Bayesian network model that you want. So here's a list of some trivial ones: an empty model, a dense model, a fairly simple Bernoulli model where connections are a constant probability row. And then you have more complex things like a stochastic block model or a latent distance model. The key point is that this model, this network model, really connects to the rest of the overall model only through the adjacency matrix. And so you can sort of choose whatever you want here as long as you have a way of sampling from it and it generates adjacency matrix. All right, so that gives you sort of a recipe for constructing a network Hawkes process. And each of the ingredients in that recipe is going to map directly on to a component type in the package. And that allows us to make this package in a nice modular design. So processes are built up from components. You have a baseline, impulse response, network models. As long as your components that you define adhere to a common minimal interface, for example, rand, resample has to implement these methods, then you can construct a network Hawkes process from those components and all of the methods that you want, like rand and estimation methods. These will all just work. And there's two sort of main points where I think this is useful: the baseline and the network. So with baselines, we have a sort of small interface. If you define your own baseline and you define the methods here in the interface, then you can use that in the continuous standard or continuous net Hawkes process, and it's going to work. There's actually a few things on here which you don't need to define if you don't want to, but the more of these that you define, the more methods that are going to open up to you in the Hawkes process. So internally, this was useful. I started by making a simple homogeneous process. The homogeneous process is nice because you have a fast analytical Gibbs sampling that you can perform. However, assuming a constant intensity isn't really a great choice in a lot of modeling settings. Just imagine that you have seasonalities in the events that you're trying to model. Constant intensity is not going to be a great choice. But then using this interface, I was able to define log Gaussian Cox process. And this is an extremely flexible model. You can choose, I have a couple kernels that I've included in the package, but you could choose your own kernels. The disadvantage of this is that it requires a sort of subsampling process for Bayesian inference, which is a bit slower than the analytical Gibbs sampling. All right, so the module design allows you to define your own baseline, and then you can plug that in. The other place where it's useful is in defining your own network. So we actually have a continuous standard Hawkes process where I don't have an adjacency matrix or a network model. It's basically just a multi-variate Hawkes process. If you want to make a true network Hawkes process, then you include an adjacency matrix and a network when you construct your model. And the sort of disadvantage here is that you lose maximum likelihood estimation. I'll talk about that in a second. But because, as I mentioned, this network is kind of separate from the rest of the model, you can go ahead and define a new network, and as long as it adheres to the following interface, plug that into the network Hawkes process, and everything will run. The networks that are currently available are a dense network and a Bernoulli network. I have some work in progress on the stochastic block and latent distance networks, but I'm not ready to put those in quite yet. All right, so that's the modular design. The other thing is continuous and discrete processes. When the events that you're studying are very dense, so basically if you have a lot of events occurring per second, a continuous process is going to get bogged down. Especially on inference. For inference, basically you have to calculate the intensity at every point where an event occurs. And because of the auto-regressive nature of the model, that means that you need to look back over the entire history of events. So this is quite slow. To get over that in practice with high density events, what you need to do is switch over to a discrete time formulation. In discrete time, you just make a bunch of time bins, and now you can put all of those events into the discrete time bins. Doesn't matter whether there's one event in a bin or 100 events in the bin now. You just need to know what's the number of events in that particular bin. And as a result, you go from something which is basically on the order of number of events squared to something which is not linear, but actually just constant complexity. So switching over to discrete time is in some cases the only real practical solution here. So we've divided the package into, so at a high level, sort of the abstract type Hawkes process. We have a continuous Hawkes process and a discrete time Hawkes process. Obviously, the continuous and discrete time processes have their own way of representing the data they generate. There's also a whole set of discrete time components that you can use as well. So things work a little bit differently there, but same basic approach. So there's two sort of main things that you'd want to do with this package. One of the things is to simulate data. Essentially, we provide a RAND function where you put in your Hawkes process and the duration of how long you would like to simulate the data for, and we can generate that. The process by which we do that is something called Poisson thinning. And if you think about how to simulate this, it's not that obvious, but the Poisson thinning gives you sort of a clever trick, well known in the literature. The idea is like this. The baseline intensity is sort of functioning independent of the rest of the process. So what we do is we start by simulating all of the baseline events. That's the dark blue dots in the image here. And then each of those events essentially makes its own little independent event, which can go off and generate more events. And so we simulate all those little events. They generate their own children, we simulate those, and we have this recursive formulation. So we run that, and then when we get done, we collect everything, sort it, and put it into a nice format. The one thing you might be wondering is, how do we know that that recursive process is actually going to to complete, so this might blow up. We provide a little function called isStable. IsStable looks at the parameters of the model. There's a very simple calculation to do on the eigenvalues, and if you check that, it'll tell you whether you actually are dealing with a stable process or not. So that's simulation. So the other, probably the most important thing that researchers are interested in is estimation or inference. The package provides three main methods for doing this. First, we start with maximum likelihood estimation. So this is fairly straightforward. We just use the optim package, standard gradient-based optimization. Unfortunately, for the network models, you can't use maximum likelihood. You have a binary adjacency matrix, so your gradient methods aren't going to work. So maximum likelihood is limited to models that you might be using as a sort of baseline that don't include a network. The main method of interest is Markov chain Monte Carlo inference, Gibbs sampling in particular. So we have an MCMC method that performs this. Every component that's in the package right now, so all the built-in components, have a resampling method, and that means that they will work with MCMC. So any Hawkes process that you could build with the built-in components, you'll be able to run MCMC sampling on. The last method we have is variational inference, a mean field variational inference in particular. So variational inference converts the inference problem into an optimization problem by making some assumptions about the posterior distribution. This method can be very fast, but it is limited to discrete models, and that's simply because we only have a formulation for it in the discrete time model. And I'll mention one other thing about that later. So we have three ways of estimating things, up to 3 ways of estimating things. And when I was talking about the interface, which of these are going to be available is going to depend upon what parts of that interface you define. So if you want to perform maximum likelihood estimation, you need to be able to define a log likelihood for your component. If you want to do MCMC sampling, you need to define a resampling method for your component. And if you want to perform variational inference, you'll have to define a variational update method. So if you have all 3 of those, you can put that component in, and you can run any of these on the resulting Hawkes process. Okay, the last bit I wanted to discuss here is multi-threading. So resampling is the main thing here. There's a bunch of embarrassingly parallel calculations in the resampling methods. In particular, for Gibbs sampling, the adjacency matrix, instead of sampling each element of the adjacency matrix individually, you can take blocks of it. In particular, you can look at a whole column at a time. Sampling those columns are independent from each other, and so we can just do them simultaneously. And the other sort of important one, the most important one here, is the log likelihood calculation, in particular for the logit normal impulse response. So as I said, in that calculation, you have to look at the intensity at every single event. And that's why it turns out to be sort of order number of events squared. However, those calculations are all independent of each other as well. So I can just go to every one of those events and say, do your own little log likelihood do your own little intensity calculation for your event and do that. And so this is going to scale very well with the number of threads that you throw at it. And in Julia, we have the beautiful @threads macro. And so with a couple lines of code, we can make this, n thread times faster, basically. So This is actually really important because, in general, all of these methods are fairly computationally intensive, and as the size of the network gets larger and the number of events get larger, this can be quite slow. So this makes practical what otherwise would be quite difficult, I think. All right, and finally, a few notes on the package status. So I have some work in progress right now. It's basically ready to be merged. I just need to do some final checks. As I was sort of preparing for this, I was looking at making some new examples. And one thing I realized would be nice is, even though this is geared towards NetworkHawkes processes, you want to compare your process to something, a baseline. And for that, it's nice to have an independent process. So a process where we just say everything in the graph is, all the nodes in the graph are independent of each other. And to do that, it's quite convenient to just make a univariate Hawkes process. So I took the same modular design and created a new univariate version of the Hawkes process definition in this package. And then I built an independent process. So you can now just directly say, I am making an independent Hawkes process. Here are the components, and do that. There are some feature requests. These are my feature requests. I'm looking for other feature requests, but I would like to finish the advanced network models, so stochastic block, latent distance, potentially some time-varying network models. The variational inference I mentioned, that's oftentimes quite fast, but we can make it a lot faster, potentially, by switching to a stochastic variational inference. We don't need to use all of the event data. We can just randomly sample some of it and run the optimization on that. So that should be a relatively simple thing to do. The other thing is exogenous covariance. This is something that every time I talk to social science people, and I say, I have this model, it's so interesting, and the first thing they say is, what about exogenous covariance? So basically, I have a baseline model, and it's sort of independent of the rest of the model. And wouldn't it be nice if I know that there's something else going on outside the environment that correlates with the intensity of the process? Wouldn't it be nice to have that? This should be fairly simple to do. It's with the sort of modular design, it's a matter of defining the correct baseline and getting the inference figured out for that. And then you should be able to plug it in. Finally, there's some utility methods that I need to put in here for evaluating models. Some help on initializing models. So for inference, we always have to initialize things first, right? And I think we could do a better job on selecting initial models or making it easy to initialize them from other models. And maybe some visualization things. All right, so that's it. There is a website for documentation, and also I want to plug the Data-Driven Social Science Initiative. We have a website as well. Check it out or come talk to me. Love to tell you what we're working on. Thanks.
So does anyone have any questions?
Do you have a running example in your mind of like what of a natural phenomenon or say like the stock market would be like a good model, and for which the ops process would be a good model?
A good application. The application I like, this is one of the applications that Linderman used in his paper, was analyzing crime. So look at a bunch of different neighborhoods in the city, get crime statistics, and see, hey, when crime's happening in this area of the city, what's going to happen? Can I forecast what's going to happen in other areas of the city? It's a very interesting application, and it's a good one.
Response functions that are continuous ones that are defined over a bounded interval, so you don't have to like loop over everything that's happened so far every time you calculate the
The answer is yes Because the logit impulse, logit normal one is actually bounded. Yeah, so that one is bounded. You specify basically what is the look back period. That's a input delta t into that. And yes, it does help, but still, it's better when it gets to really dense events. It's better to have the parallelism. Yeah.
You were mentioning the cat threads macro. There's been a lot of discussion about that recently. You considered any of the other threading packages as a way to parallel your code?
I have not explored anything else, and I've had a lot of success using that macro. So for this application, it's fairly straightforward and works very well. So I'm happy with it. Yeah.
So when so you have some data and you try to, say in the case of the crimes, and you're trying to, is it possible to estimate what is the impulse response? Like how much, say with the likelihood method, or how much can you try to estimate the parameters of your model?
The whole thing is estimated. So the only thing I'll say about the impulse response estimation is, in some cases it isn't the likelihood basically isn't that responsive to the impulse response, and so you can come up with estimates that aren't that meaningful. I think in some cases, it's just that the baseline and the weights tend to sort of dominate. That's what I sort of empirically see.
Agency matrix underlying the process is easy to estimate, like say easier, or the likelihood is a bit sharper than the impulse response?
Is the adjacency matrix easier to estimate? I don't know if I have I have sort of observed that it doesn't tend to sort of give you probabilities that are very close to zero. So it seems that there's partly because you have to choose a prior for this, right? So maybe with the correct choice of prior, you'll be able to push those probabilities down a little bit more. But mostly what I see is like, if there is a connection, it's gonna give you a probability of 1 or very, very close to 1. And if there's not a connection, maybe it'll be like 0.5. Yeah, but it struggles to push it far down.